Wow, how clumsy do these numbers look? There's so many zeros. Up here, there's so many of them. Very big number. Down here, lots of zeros, very, very small number. That's a bit messy. Is there something that we can actually do mathematically to make these numbers look a bit neater? Let's have a look. And it's called, as you knew from the presentation's name, scientific notation. A way of making some of these very large, there's one, and very small numbers look neater. What is this? I don't know, 75 trillion or something. And that's approximately the number of cells in the human body. And down here, what's this? About the number of grams in a glass of water that's been chlorinated. Okay, so what could we do? Well, it's at the end of the series on powers. So look at that, there's 3, 6, 9, 12 zeros. So we could call that 10 to the 12th. When you multiply a number 75 by 10 zeros, that's 10 times itself 12 times. So that's the old power stuff, index or power rules. What about down here? What's happened to 475? Well, we could say this time it's been, 475 has been divided by, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's divided by 10 to the 9th. 9 places. Each place to the left means division by 10. And so there we have it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. But we know with index laws, this is 475 times 10 to the -9. Negative exponent means all the 10s are in the bottom line there. We're dividing by them. Do you remember all that stuff? That's pretty important. So that might give you an idea, because we can package our zeros up in this neat index form. Okay, well, let's have a look. We usually have a common system though. We don't use 75 or 475. We use a number between 1 and 10, inclusive, multiplied by a power of 10. So if you want to get really mathematical, it's a times 10 to some power, and this will be a negative if we want to make the number smaller and have zeros in front of it, and the a value will be between 1 and 10. It wouldn't be equal to 10. See that it's not equal to 10, because that would be the next power of 10 there. So you'd add one more to the power of 10. And we always use k as an integer. It's a whole number as the power of 10. Let's have a look. So here's one like before, and this is 4,500,000. So what are we going to do? We're going to start off with 4.5. Okay, so 4.5, I'd rather do it differently from what they've got here. 4.5, you'd have to shift the decimal place across there by 6 places, and they're counting back. I'm going to count forward. Put the decimal where you want it for a number between 1 and 10, 4.5, and then count up how many decimal places to the right, each representing 10. You would have to move it to get the actual given number. So it's 4.5, choose a number between 1 and 10, and then the power of 10 necessary. What about this little dude here? So we'll start with a number between 1 and 10 in there, and not right at the end like I did above, not down there, but a number between 1 and 10 so they all look the same. And then we've got to count the places in that we want to shift it. And that's 4 places to the left, so it's division by 10 to the 4th. Or you can call that multiplication by 1 over 10 to the 4th, and 1 over is the negative power. So can you see that's a very, very handy way of actually getting rid of all those zeros and making the number look neater. So I want you to try these down here, and I'll show you the answers a bit later on. But try to write those using our scientific notation up the top here. Scientific notation, number between 1 and 10. So assign that position, put it in there, in there like that, and then work out what power of 10 you need to create the number that you were actually given, the clumsy looking number. Okay, it's great for writing very large and very small numbers in a neat or efficient way. Right, so pause the presentation, have a go at that question, and come on down now. Here's some that are practical. The distance from the Sun to Mars is about 240 million kilometres. Okay, lots of zeros there. So you've got there some situations in everyday practical ways of making numbers neater. Okay, those practical numbers, making them neater. So have a go at those, and we'll go on here, and I'll give you some answers in a minute. If you want to get your answers, you could scroll forward a bit. So now it's going backwards. Here is a number in scientific notation form. So it's 3.2 by 10 squared. So 10 squared means multiplying by 10 once, twice. So it's 320. You can leave that line out if you wanted to. 5.76 by 10 to the minus 5 means you're dividing by 10 to the 5. Negative exponent means 1 over, or the reciprocal. So it's 1 over 10 to the 5th, which means it wasn't really this big. You have to move it down here 5 spots. So the answer is 0.40576. Okay, so you get the idea. You've got to, once you go into this notation, you've got to remember what the actual size of the number would be without us making it neat with scientific notation. So it's important to be able to go backwards. All right, have a go at this little set here now, and pause it, and we'll come and have a look at some answers in a minute. Okay, last two questions. Right is an ordinary decimal number, more of those, and here we are. Here's some practical ones. Wavelength of blue light, or the world population for 2010 was that. How many people is that really, with all the zeros included? So have a go. We're trying to be able to work both ways to make numbers with lots of zeros in them neater, but also to be able to come back and realise how big or small they really are. Okay, so here's your answers here. Questions 3 through 7. I hope you did pretty well. If you were a bit puzzled, go back and have another go and see how you might get that answer. Let's go on now and doing a few little things again with our new system. So if we are in this system of powers of 10, scientific notation, we want to be able to work out perhaps sizes of numbers. So here, which number is larger? Well, this part of that one is larger than the equivalent part of that one. But look at the extra power of 10. We're multiplying by 10 to the 4th or 10 to the 5th. So which will be larger? It's the one with the highest power of 10 will be larger, because a power of 10 means it's 10 times bigger. And then what about these two little ones here? 2.6 by 10 to the minus 4 or 2.7 by 10 to the minus 4. They've got the same power of 10. They've both been divided by 10 to the 4th. But because the number this time out the front is bigger, that's bigger than 2.6, so this is going to be bigger than the other one when they've both been multiplied by 10 to the negative 4. Okay, so the power of 10 is pretty important in working out the size of the number, because every power of 10 means it's 10 times bigger or 10 times smaller, depending on whether you're multiplying or dividing. So here's some questions for you. Which is larger? Whip through those and see what you think, and then mark your work. Okay, we'll have the answers in a minute. Simplify the following, giving you answer in scientific notation. Well, here we are. We've done this with powers before. It's numbers together, and there it is, and then powers together. So overall, it's 20 by 10 to the 9. But we don't have 20, do it? It's a number between 1 and 10. So that's 2.0 by 10 to the 1. That's changing the 20 to scientific notation. And we already had 10 to the 9 from the power rules, multiplications of numbers that are written as power of the same base. You add the powers. So overall we've got 2 by 10 to the 10. Fair bit of work in that. What about this one over here? We're dividing. So 8 divided by 2 is still always 4. Usual way with numbers. Don't get confused. With powers, however, it's subtraction of powers. So it's 10 squared. Okay, so it's mixing it up a little bit, like we did with our index laws, mixture of numbers and powers. Pause the presentation and have a go, and we'll go on. There are the answers for you there, 8, 9 and 10, and see what you think of those. I think I left out 9 because that was an opening problem, and I didn't include that in the clips. All right, let's go on. On the calculator. This is very important because when you get big numbers on the calculator will automatically go to scientific notation. Let's see what it looks like though if we want to do this multiplication on the Casio. So here it is, 1.67. Now how do you represent 10 to the 4th? Where do you get that E from? So come across over here, right over here, see that? That exponential there means exponential or power of 10. So you just have to hit the X button and then 4, and that'll give you 10 to the 4. Times, because we're times it, 2.3, and we want this power of 10, so that's going to be E to the 7th. Using this button down here, the exponential button. That exponential button means powers of 10, or an exponent of 10. And then the calculator will stay in scientific notation form and give you 3.841. E to the 11th means times by 10 to the 11th, doesn't it? Okay, so you can get the calculator to work in that form. So let's look at this second problem here. 9.49. And now it's E, which is power of 10. You must have negative because it's 10 to the neg 3. And now we're going to divide by 2.6. And here again, E to the 6 this time. So it's a positive power. When you multiply those together, we're dividing here. You divide them, it's 9.49 divided by 2.6. Comes out to that, and then the calculator will tell you the resultant power of 10. That means 10 to the neg 0.09. Okay, so it's a very, very, very small number. So just write what's there now, that when you see, because you might not put it in scientific notation, you might put a big question in like this, times by, I don't know, 3,000. And if you put that on the calculator, it's going to come out as 7.5 by, oops, we have to go back there, 7.5 by 10 to the 7th. By 10 to the 7th. And on the calculator, that would come up as 7.5 E7. So don't get confused. It doesn't put that power of 10 in. Okay, but it'll do the multiplication to get 7.5. And then it will have E7. All right, how are you going? Let's go to the calculator now. This is the Casio, and other calculators also have a similar function, a similar setup. So have a look at those. Here we go. A set of exercises here where you're going to do this on the calculator and see what you come up with. Okay. Pause it, have a go, and I'll come up with some answers in a minute. And there they are. There are answers for those last few problems. So I hope you've enjoyed this little use of scientific notation or power work. And it does make large numbers very much easier to understand and neater. So I hope you've enjoyed it. I'll catch you in another presentation. Cheers for now.